All right, so the plan for today is to finish up chi-square test, the test for independence, and then discuss the analysis of variance. So that should take us through the rest of class today and finish up the material for the course. And then we also have, just remember, an optional review session on Wednesday, 10:30 to 12:30. Again, we just have to do something during that time frame, so I'll just treat that kind of like office hours. If there's only a couple students, or if more than a couple folks show up, then we can do, a more topic-based review. But if you have any questions or you want to pop in anytime during that time, feel free to. Of course, you can always email me too if you have any questions this coming week. I won't have normally scheduled office hours, but just this review session, or of course, email if you have any last questions. And then this week, the final exam is already available. So it's up and available. It's on my stat lab. You can log into Examity, same way that you did with the midterm exam. I've said this a couple of times already, so I won't belabor the point. Sample final exam has been available for quite a while. And the formula sheets are available on Blackboard under the supplemental material exam material folder. So you can either save those as a PDF to your computer and use it as a PDF while you're doing the exam, or you can print them off, or you can use it both ways, whatever works best for you. And as I mentioned before, I strongly recommend completing the exam on Wednesday at the latest. I would not recommend waiting until Friday. Certainly, Thursday is cutting it a bit close. If something does come up, an internet problem, a computer problem, something like that, if you have a day or two to work out that issue or get in touch with me, we can find a solution. If you wait until the last minute, that's taking a pretty significant risk with your grade. Okay. Yeah, a couple of questions in chat, a couple of questions I answered already. But yeah, so question in chat, correct. There's no office hours, no regularly scheduled office hours this week because it's finals week. So like my usual Tuesday, Wednesday, Thursday office hours won't be on this week. But if you have questions, you can always send me an email. Yeah, if you want to make an appointment, send me an email. This time of the semester is typically somewhat busy for me, but I can probably squeeze in a meeting if anybody wanted to set up a meeting. So yeah, just send me an email and we'll try to make something work. Like I said, I mean, end of the semester is always a little crazy for everybody, but I'll do my best to make something work if we're able to. So just shoot me an email if you want to meet this week. I think that is everything in chat. Any other questions that anybody has? Okay, then we will get into it. Just because of the way I copied things over, OneNote sometimes doesn't like to copy super easily, so we're gonna jump down to the bottom of this OneNote file for chi-square tests, and then come back up to the top for ANOVA. So scroll down here. Okay, so talking about, and let me give myself actually a lot of room here because I might want to get a little extra room for the ANOVA if I need it. Okay. Okay, so moving down to chi-square tests for independence. So remember last time we had talked about chi-square tests for goodness of fit, and just super quickly, I'll remind us what we discussed. The chi-square goodness of fit test, the idea was we had a hypothetical distribution with some probabilities, maybe P1 through P6, maybe for a six-sided die. These were our maybe expected probabilities. This led to expected frequencies. So we had E1, E2, and so on through, say, E6. This was the number of die rolls. If we say roll a die 100 times, this would be the number of ones that we would expect and twos that we would expect and so on, if our hypothesized frequency distribution was correct. We had observed frequencies from the actual experiment. We actually rolled the die 100 times. We counted how many ones we got, how many twos we got. And we said, kind of generally speaking, if the O's are close to the E's, roughly speaking, if those numbers are pretty close together, then it seems like our hypothesized distribution maybe is a reasonable model for this situation. If the O's tend to be pretty far away from the E's, then maybe our hypothesized model isn't such a great model, and maybe we'd want to go with something else. So we have a chi-squared observed that looked like observed minus expected. So it looked like that difference between the observeds and the expecteds. But again, this is signed. It's going to be positive sometimes, negative other times. If we just add these together like this, then they're going to kind of cancel out. So we take observed minus expected squared, and that makes everything positive. So that whether the deviation is that the observeds are a little higher than we expect or a little lower than we expect, that still counts in the same direction. And then just to kind of make the probability theory work out right, we have to divide by the expected. So we have observed minus expected squared over expected, and we add all of those up. The larger this number is, the larger the typical difference between the observeds and the expecteds, and the less comfortable we are using our hypothesized model to model this situation. So for a big chi-squared observed, that would put us far into the right tail. That would be a rejection. And what would a rejection get us? It would get us that basically that this model is not a reasonable model. Therefore, the null will be that, say, probability of rolling a 1 is P1, and so on through probability of rolling a 6 is P6. Basically, that our hypothesized model is correct is going to be our null. And our alternative is basically going to be not this. At least one of these probabilities is different than what we hypothesized over here. And again, if chi-squared observed is bigger than chi-squared critical, we reject H0 in favor of H1. We conclude that there's too much of a discrepancy between what we would expect to see under our model and what we did actually see under the experiment, and we're not comfortable using that model. We reject that model in favor of saying that maybe a different model would be a more appropriate model, and we don't think that that model is a good fit for this data. Now, this is important because this same idea is going to be applied to the chi-square test for independence. Okay, so let's suppose that we have two variables, x and y. These are categorical variables, sometimes called factors. These are things like qualitative variables, things like colors, something like that. And suppose that they have different possible outcomes, which are sometimes also called levels. Unfortunately, in some of these applications, and we'll see in ANOVA as well, because there are a lot of different social sciences that use these techniques, sometimes there are different, there's slightly different language that is used depending on what situation you're in. So sometimes factors versus levels, sometimes we call them variables versus outcomes. But let's suppose that X has R distinct outcomes and Y has C distinct outcomes. Let's look at what some data for this might look like. So for instance, we might have, let me get myself a little more room here. we might have, for example, clothing type. And let's say that the clothing that we're interested in is just shirts versus pants, and color. And maybe we live in a more boring society where it's only red or green for the color. So we could imagine a grid like this. Now we have a 2x2 grid. I mean, of course, we could have, in a different situation, more types of clothing or more colors. So we could have a larger grid, but just to keep things manageable, we're using a small example. And let's say of people that we observe with who are wearing a certain piece of clothing that's a certain color, we see 3 red shirts, 17 red pants, 67 green shirts, and 13 green pants. And we might be interested in knowing, so what's our question that we're trying to answer here? We might be interested in knowing is color independent of clothing type. Do I think that a person is as likely to choose red versus green for shirts as they are for pants? Or do I think that, given that a person is picking out a shirt, they're more likely to choose one color than if they're picking out pants, they're maybe more likely to choose a different color? Do I think that the probability of one color versus another conditioned on the type of clothing changes? Or do I think that's just consistent across the board? That's the question we're trying to get at here. Now let's think a little more abstractly about this. Let's suppose that we had, maybe I'll actually switch colors for this just to make it clear that this is a different point that I'm trying to make here. Let's suppose we had a different grid. And here we have 2 variables, X and Y. And I'm going to name them the opposite way just so that everything is consistent with how I have it written here. It doesn't matter which one goes on which. We'll call this Y and this X, mainly because I said that X has our outcomes up here. So that way I can keep all of my notes associated the right way. So X is associated with R rows, which is why it's an R, which is why I wanted to make sure that my variables were going the right way. And Y is associated with C columns. So Y has C different possible outcomes. Remember, it's categorical, it's qualitative, so we can enumerate all of the different outcomes. And X also has distinct outcomes. It has R different outcomes. So I can make a grade similar to what I did up here, but here I'm, I could have 10 outcomes and 3 outcomes, or 7 outcomes and 6 outcomes. I could have a variable number of outcomes for each X and Y. Now, if I think up here, if I have my observations, what is fixed about these observations? Well, what's fixed is that I have 70 shirts and I have 30 pairs of pants that I observed. Or in other words, I have 100 total pieces of clothing that I observed, or I have 20 red pieces of clothing I observed and 80 green pieces of clothing I observed. I got that just by adding the rows and adding the columns and then getting a grand total for that 100 down in the corner. So what I know is that I have some row sums and some column sums. So I have, for instance, maybe I'll just call this like R1, R2, down through, I have R, oh, I don't want to use R as the variable again. Maybe I'll call it little x1, little x2, down through little xr minus 1 and little xr. Those are my row sums. And then I have some column sums. Let me call that little y1, little y2, down through little yc minus 1, the c minus first column, sum, and little yc. And then down here in the corner, I have a grand total. I'll just call this n, the total number of observations. That's just the sum of all of the cells in the grid. Now, let's see if I can do this. I don't use highlighters often in here, so fingers crossed that this works pretty well. But if I consider these row sums, column sums, and grand totals as essentially fixed, the same way that if I had a one variable set of observations, I would consider the total, say, number of die rolls in the previous example fixed. Here I'm kind of considering each row sum and each column sum as being fixed. Then I see that my degrees of freedom actually look like I'm able to choose C minus 1, say, columns from the first row, however I want, as long as I leave one column left at the end of the first row, I can match my row sum if I need to, right? I can pick this last one however I want. In the second row, I can choose the first C minus 1 columns any way that I want. Again, as long as I leave that last column in the second row, then I can use it to match the second row sum and so on. So I need to leave off one column for my degrees of freedom from the things that I can freely choose. And similarly for my column sums, to match my column sums, say in the first column, the leftmost column, I can choose the first r minus 1 rows in that column any way that I would like, as long as I leave this one at the end here to match my first column sum, and so on down the line. So I can choose the first r minus 1 rows any way I want. In other words, I can choose this grid here I can choose these data any way that I like. I just have to leave one row and one column in order to make the row sums and column sums match. Or in other words, I have my degrees of freedom, degrees of freedom here. It's not just n minus 1, which before, remember, that would have been like the number of possible outcomes minus 1. In this case, it's going to be the number of entries in this box here, but this box is r minus 1 by c minus 1. So I need to use a slightly different degrees of freedom here. This is the first time that we've really seen a different degrees of freedom. I mean, I suppose maybe a little bit in the comparing two means, but we kind of glossed over that and just said use the smaller of the two for the degrees of freedom. But here we have our first kind of, actually complicated degrees of freedom that we need to calculate. But it's not too bad of a calculation. We just subtract 1 from the number of x outcomes, subtract 1 from the number of y outcomes, multiply those two together. That gives me a number, and that's my degrees of freedom. Okay, so let's take this grid here. I'm going to see if I can just copy it down. That'll work. I think that got everything. All right, good. So let's look at this example. We're interested in knowing whether clothing type is independent of color choice. And these are our observed data. So in other words, what we see is the empirical, say probability of red and shirt is what? It's 3 red shirts that we observed over 100. That's the probability that we'd estimate from the data. What is our theoretical probability of red and shirt, or our expected? Probability of red in a shirt. Well, here we are operating under the idea that assume H naught is true. H naught, the null hypothesis is that these are independent, and H1 that they are dependent. Why are we assuming they're independent? Well, because then we can say this is the probability of red times probability of shirt. Right? If color and clothing type are independent, then the probability of A and B is just probability of A times probability of B. That's essentially what it means to be independent, right? But what would that look like? That would look like, well, probability of red is 20 over 100. And probability of getting a shirt is 70 out of 100. Or this is going to be 2 times 7 is 14. So that's 1400 over 100. And I'm going to write it as times 1 over 100 this way. Or we can see that this is going to be 14 over 100. So I have a set of observed data in this grid, but I could make a similar grid, shirts and pants, red and green, clothing type, and color. I can make another grid to stand alongside this that is the expected data. In other words, expected under the null hypothesis of independence. Now, in this expected data, again, I need to have still 70 total shirts and 30 total pants. Those are fixed. And I need to have 20 red colored pieces of clothing and 80 green and 100 total pieces of clothing. And I can see that the expected number of red shirts that I would get if these are independent is 14. This would give the probability of 14 over 100, right? This 100, I'm just kind of plucking off because that's that 100 denominator there. So we see that we would need 14 red shirts, or we would expect 14 red shirts if these were independent. We actually observed from the real world, from our empirical evidence, from our data, we observed 3 red shirts. We can do this for each of the boxes in the grid, and then again, we can go back to this general idea where we say, I have some expected boxes, I have some observed boxes. If the observed boxes are kind of more or less look like what the expected boxes have in them, if the two distributions in a sense, or if the two grids look pretty similar to one another, then I'd be pretty comfortable just sticking with the null hypothesis that they are independent, that the data that I got are in line with what the data might look like if they would be independent. On the other hand, if I see a great deviation between the two, if I see that my observes, my actual data, really doesn't look much at all like what I would expect if the variables were independent. In other words, if I see that the contents of the observed data boxes look very different from the context of the expected data boxes, then I'm going to be less comfortable with moving forward under the presumption of independence, and I would reject the null in favor of the alternative and maybe conclude that the variables are dependent. So we can see how this is very closely mirroring our setup for the chi-squared goodness of fit. This chi-squared test for independence is really just the chi-squared goodness of fit for these kind of box, this kind of box setup here. Okay, so the next thing we have to do is really just fill in the rest of our expected data. And then we have to assess whether we think that the observes are far away from the expecteds or close enough, whether we should reject the null or fail to reject the null. But we kind of see how to get the expecteds now from this example. So my expected is, it looks like the number of red over n times the number of shirts. And I wanted to get rid of one of these hundreds because here I've computed a probability, but I don't want a probability, I want a number. So I need to multiply by 100. So I just basically get rid of one of these denominators. So to find what should go in red shirts, I just ended up doing number of red, 20, times number of shirts, 70. That gave me 1400, and then divided by n just once though, divided by 100, which gave me 14. So for the expected number of, say, red pants, what would I do? For this number, I would say, well, number of red is 20 over 100 times total number of pants is 30. 20 times 30 is 600, over 100 is 6. I just multiply my row total times the column total, divide by n, but just once, and that gives me the number that I'd expect in that box. If I divided by n twice, once for each of the two numbers, then I would be left with a probability with a proportion of the data that I would expect in that box. But I want the number that I expect in each box. For what, maybe green shirts next, I have 70 shirts divided by 100 once times 80 green colored pieces of clothing. 7 eighths are 56, so 5600 over 100 is just 56. And then similarly for the green pants, I have 30 total pants over 100 times 80 total green color pieces of clothing. That's 2400 over 100, or 24. Another way of looking at what I'm doing here is I'm saying if these are independent, I can apportion my green colored clothing proportionately between shirts and pants. I know that overall 70% of clothing that I looked at are shirts and 30% are pants. So if these are independent, then 70% of my green clothing should be shirts. That would be 56 shirts, 56 green shirts. And 30% of my green clothing that I saw should be pants if they were independent. So 30% of that 80 is 24. So that's zooming out a little bit. That's really kind of what we're saying here. We kind of just followed our nose with the calculations and came up with this procedure, but we can see the logic of this procedure. We're just saying if these are independent, then the apportioning of, say, green clothing to shirts versus pants should be the same as, should be proportionate to the overall apportioning of shirts versus pants. Okay, so let me clean this up a little bit, just because we've got a lot of scratch work going on here. And I think I'll actually get rid of these as well. Okay. So at this point, what do I have after all of that work? What I have is, again, on the right in the blue, I have kind of a, under the null, a theoretical kind of perfect sample from an independent distribution here. If clothing type was independent of color, and I had 70 shirts, 30 pants, 20 red pieces of clothing, 80 green pieces of clothing, 100 total pieces of clothing, this blue distribution is what I would expect. This is what I would expect my frequencies or my data to look like. On the left is the actual observed data. I actually went out into the world and did an experiment, and this is what I got, 3, 17, 67, 13. It doesn't look exactly the same as the blue, but then again, the question is, could this reasonably have occurred by sampling error? Could the distribution actually look like the blue one? And I just got a few fewer red shirts than I might expect and a few more, say, green shirts than I might expect just by chance. So to assess that, what do? Well, we calculate, and let me rewrite my assume H naught is true. Erase that. So let's rewrite that just to be clear what we're doing here. I go through and I calculate my chi-squared observed. And again, these are observed versus expecteds. 3 versus 14, 17 versus 6, and so on. My chi-squared observed looks the same. It's observed minus expected squared over expected for the same reason that we discussed before. And I add those up. So for instance, I have 3 minus 14 squared over 14 plus 17 minus 6 squared over 6 plus 67 minus 56 squared over 56 plus 13 minus 24 squared over 24. So let me switch my share now. Do one thing here really quick. Didn't have my chi-squared table open. Okay, so that's open now. All right, so I want to calculate this thing here. So this is what? 3 minus 14 squared. Well, that's 11 squared, or 121 over 14. Plus 17 minus 6 is also 11 squared, 121 over 6. 67 minus 56 squared, that's also 11 squared, or 121 over 56. I made this easy for me to do. And 13 minus 24 squared is also 11 squared, or 121 over 24. So it just happens that all the numerators are 11 squared, or 121. So I don't have to think too hard. And this gives me a chi-squared observed of about 36.01. Now remember, the larger chi-squared observed is Generally speaking, the further apart my observes tend to be from my expecteds, the less confident I am in my hypothesized distribution, or my hypothesized characteristic in this case, of independence. So this is a right tail test. So what's my chi-squared critical? And as always, we're going to use 5% for alpha here. So I need 5% area and right tail. And then what's my degrees of freedom? Remember, it's a little more complicated here. We have, where did I write it up here? We have a formula that's number of rows minus 1 times number of columns minus 1. Or I have 2 rows and 2 columns. So my degrees of freedom is 2 minus 1 times 2 minus 1, or 1 times 1 is 1. I'm looking for 5% area to the right on a chi-square distribution with 1 degree of freedom. Okay. So I'm looking for area to the right of 5%. That's in this column. With 1 degree of freedom is 3.841. And remember, this is a right tail test, because again, chi-squared observed tends to be large when my observes are very different from my expecteds, when my actual data does not match up with the null hypothesized distribution, or in this case, characteristic of independence. So I can now clearly say, since chi-squared observed of 36.01 is bigger than, is to the right of 3.841 chi-squared critical, we reject the null in favor of the alternative, and we conclude clothing color is not independent of clothing type. So we can really see how this chi-square test for independence is really basically just a goodness of fit test, but it's just a question of, does the fit of the distribution, what it would look like under independence, is that a good fit or not? So our expected data over here is what our distribution would look like if the row and column totals were the same and we had independence. So what we're saying here is we don't think that this data could reasonably have occurred just by sampling error from a distribution that is actually independent. We think it's too far away. All right, any questions on this?
Can you explain the last part once again?
Yeah, sure. So yeah, let's run back through this. So we assumed H naught is true, just like we always do with any hypothesis test. And then we want to compute a observed value versus a critical value. So we're using the critical value method here. Chi-squared observed is the sum of the observed minus expected squared over expected. That was our previous formula, so same formula here. The idea being that the further apart the observed datas in these cells tend to be from the expecteds. The further apart those are, on one hand, the larger their squared difference is going to be, giving me a larger chi-squared observed number. And on the other hand, the further apart they are, the less confident that I would be, supposing that this data actually does come from a distribution that's in, or does come from a situation where we have independence between the variables. So the larger the differences are from one cell to another, the more strongly I want to reject the null in favor of the alternative and reject the idea of independence. We got this, this expected data over here by imposing independence on these row and column totals. So I compute my chi-squared observed by just taking the differences, say 3 minus 14, squaring them, dividing by the expected number, 3 minus 14 squared over 14, and then doing that for each of my 4 cells. So for the red shirts, observed minus expected squared over expected, 3 minus 14 squared over 14. Doing the same thing for the red pants, for the green shirts and the green pants. We add all those up and we get a chi-squared observed of 36.01. Very similar to like a Z observed or a T observed that we might have gotten in, say, chapter 8. We know this is a right tail test because, again, we want to reject whenever the observeds are very different from the expecteds. And when the observeds are very different from the expecteds, that observed minus expected squared is a large positive number. So the more large positive chi-squared observed is, the more we want to reject. So this is a right tail test. We have chi-squared observed. We see that it's a right tail test. It's a one tail test. We need to figure out chi-squared critical now. So what is our critical number, our critical value that we're going to test our observed value against? To get chi-squared critical, we need 2 things. We need to know what is the area to the right, and we need to know the degrees of freedom, and that tells us what our chi-squared critical is. It's a right tail test, so, and we're just using 5% because unless otherwise stated, that's what we'll use. So it's a right tail test, and we put all of that area into the right tail. So 5% area in the right tail. And my degrees of freedom, that was from up here. Remember, we need our row and column totals to be the same. So we need to lose 1 column and 1 row from the degrees of freedom from our unconstrained choices so that we can make those row and column totals match. We can use that that 1 line down here, or that 1 column over here to force the row and column totals to match, but we can choose all of the rest, R minus 1 times C minus 1 boxes. So my degrees of freedom are rows minus 1 times columns minus 1. Or in other words, really the only thing I could do is say, for instance, choose red shirts. If I decide that there were 20 red shirts, then there have to be 50 green shirts to make a column total of 70. And if there were 20 red shirts, there would have to be, I guess, 0 red pants to make a row total of 20. And with 0 red pants, there would have to be 30 green pants to make this column total of 30. So we really only have 1 degree of freedom here, which is 2 minus 1 times 2 minus 1. Once we plug in a number for any one of those boxes to get the correct row and column totals, everything else is determined. We only have 1 degree of freedom. So our chi-squared observed, 5% area to the right, 1 degree of freedom. There's my 3.841 for my chi-squared critical. My critical value 3.841. Now, since it's a right tail test, I ask, is it true that chi-squared observed is bigger than chi-squared critical? In this case, yes, it is. Since chi-squared observed is bigger than chi-squared critical, it's in the rejection region. It's in the right tail. Then we reject H0 in favor of H1. We reject the hypothesis of independence between the variables in favor of the variables being dependent. So we conclude that color is not independent of clothing type, that there is a dependence between these 2 variables, color and clothing type. So did that help clarify a little bit? I think it was a good idea to go back through that logic.
Yes, it did. Thank you so much.
Okay, sure. Any other questions?
Professor, just 1 quick question, Professor. Well, I did see how you did find the 14, but I just forgot that one, from the expected value data table. Could you please go over that one more time, like how you get a 14 on the expected data value?
Yeah, sure.
Thanks.
So the basic idea is this, that if my clothing color and clothing type are independent, then I see that we could look at it this way. We could say, well, clothing type overall, we have 70% are shirts and 30% are pants, which I get from 70 over 100 and 30 over 100. So overall, I see that 70% of the pieces of clothing are shirts and 30% of the pieces of clothing are pants. Now I see that I have a total of 80 green pieces of clothing. If these are independent, color versus clothing type, then I'd expect 70% of 80. This is the number of, say, green and shirt that I would expect, or the number of green shirts that I would expect. 70% of 80 is 56, or the one that you particularly asked for was the red shirts, the 14. Same idea here, is the number of red and shirt. Well, if these are independent, then I should have 70% of 20 being red shirts, and 70% of 20 that's my 14, that's my 56. And realistically, if I find one of these, once I find 14, I know that my row and column totals have to be determined. So once I find, say, 14, I know that 14 plus the number of red pants has to give me 20. So this has got to be 6. I know that 14 plus the number of green shirts has to give me 70. So that's got to be 56. And then I know, for instance, that my pants total has to be 30. So like 6 plus 24 is 30. Really, once I find one of them, I can find the others just with subtraction. The way that I did it, I just found all of them kind of the same way. But yeah, so the way that we would find, say, this one, for instance, is taking 70% of 80, or sorry, 70% of 20. Or alternatively, we could have taken 20% of 70. Either way, 70% of 20 or 20% of 70 gets me the same answer.
Yep, that makes sense, Professor. Thank you.
Yeah, sure. Yep. Okay, any other questions on this one? Okay. So again, chi-squared test for independence. Once we get the grid written out with the observed grid versus the expected, it does have pretty much the same feel as a chi-squared goodness of fit from that point on, with just that difference in the degrees of freedom. Okay, so for the last bit, let's talk about ANOVA. And obviously this recording will be posted on YouTube, but I also have another recording for both of these on YouTube also, that I posted a supplemental recording. So if you wanted to revisit just one of these topics, you could pull up one of the supplements as well. Or if we don't get quite all the way through ANOVA, I think we will, but just in case we don't, then you can check out the last little bit of the lecture on the ANOVA supplement. So ANOVA stands for analysis of variance. And again, this is a pretty big topic, kind of like correlation and regression. There's a lot that could be gone into here. And we're just going to scratch the surface, mainly for two reasons. One is that it's just an interesting idea, and it kind of brings together some of the topics that we've talked about throughout the course. And two is that it's actually used in a lot of social sciences. So, if you're going into anything related to social science, chances are that at some point you'll see an ANOVA used. maybe in a journal article you're researching, or maybe in research that you're doing even. And at least having an idea of what it is and how it works is a really good jumping off point for that. This is certainly not going to get you fully up to speed on what ANOVA is, but this at least gives you hopefully enough information that you can, if you need to, dig into this a little further and have a little bit of an idea of how things work. So we're looking at one-way analysis of variance. And the goal, seemingly kind of strangely, is to determine whether the means of several populations are equal. So that's the kind of interesting thing here. We're looking at variances to try to say something about the mean. It seems counterintuitive, but we'll see how that works. So our goal is, again, typically we're thinking we have 3 or more populations, and we want to determine whether the means of those populations are equal in light of some sample data. If we only had 2 populations, we'd probably just use like a chapter 9 testing for the difference between means type of test. So again, our strategy is that we're going to use information about the variances to make inferences about the means. As I note here, we're only going to discuss the case of 3 populations, but this is really just a notational convenience. Everything generalizes to more than 3 populations, or even for that matter, 2 populations. We'll see an example actually that the 2 population ANOVA really is just the same as the t-test for a difference between 2 means. So we'll see that in one of the examples. But we're just using the case n equals 3 populations, because that gives us enough meat to work with, where this is an interesting problem. It's not a problem that we could have addressed in, say, chapter 9. But we just don't have a ton of cumbersome notation to deal with. So what is our null? Our null is that the 3 means are the same. That the mean from population 1, from 2, and from 3 are all the same number. And the alternative is that at least one of the means is different from at least one of the others. Our alternative could be satisfied if, say, maybe mu1 and mu2 were equal, but mu3 is a different number. Or it could be satisfied if all 3 of them are different numbers, right? If we have 10 populations we're looking at, you could imagine there's lots and lots of different possibilities for not all of the means being the same. So our alternative is not saying that every mean is different from every other mean, but it's saying that there's at least one mean that's different from at least one other mean. So with a lot of means, there could be a lot of possibilities for the alternative hypothesis. But the null hypothesis is always that the means are all the same. I think this is the most important picture in ANOVA to really tie together the idea of why we're looking at variances to say something about means. Let me actually switch my share back to just OneNote. There we go. That way it'll show up a little bigger on your screen. So there's this idea in ANOVA where we're looking at variances in kind of from two different perspectives. We can take each of the 3 populations independently. We have a data set from population 1, a data set from population 2, and a data set from population 3. We can look at each of those data sets independently and look at what their variance is. So if I look on the left here, I might see, the blue population has some kind of, decent, like reasonable level of variance. So does the red, so does the green. They all have kind of a moderate amount of variance, let's say. But also their means, x bar 1, x bar 2, and x bar 3 are all kind of close together. So if I consider those 3 data sets, 3 distinct data sets that each have kind of a moderate amount of variance moderate amount of variance for each of them. But then what if I took those three data sets and combined them together into just one big data set? And if I looked at the variance of that one big data set, it would also have pretty much a moderate amount of variance, right? There's not a ton of really big outliers, whether we consider each population individually or whether we aggregate them and consider them as in an aggregate. So this would be an example that where we might see data like this coming from a situation where the means are all the same. X bar 1, X bar 2, and X bar 3 are all, fairly close together. Not exactly on top of one another just because of sampling error, but pretty close together. So the overall mean, the aggregated mean, or sorry, the aggregated variance looks a lot like the individual variances. Now let's consider a situation on the right over here where we have one mean, mu1, that is different from the other two. So mu2 and mu3 are the same, but mu1 is different. So mu1 is way to the left of mu2 and mu3, and therefore x bar 1 is way to the left of x bar 2 and x bar 3. That's what we would expect to see from the data. Again, if I look at data set 1, I look at its variance. I mean, that's the blue bell curve here. Reasonable, moderate amount of variance. If I look at x bar 2, the green curve here, or data set 2, centered around x bar 2, again, the green curve, moderate amount of variance, no crazy outliers. My red curve from data set 3, centered x bar 3, reasonable amount of variance, no big outliers. If I look at data sets 1, 2, and 3 individually, they each have kind of a reasonable, moderate amount of variance. But remember that outliers dramatically increase variance, right? Outliers have an outsized effect on variance. If I put all of these data together into one big data set, then what am I going to have? I'm going to have, like, say, let's say roughly 2/3 of the data kind of globbed off here to the right, and then like 1/3 of the data way off here to the left. This 1/3 of the data maybe is going to look like outliers relative to the other 2/3 of the data. When I combine the three individual data sets into one big data set and look at the variance, I'm going to have a chunk of data off to the right, and then what's going to look like a bunch of outliers off to the left from their perspective. That's going to dramatically increase the variance. So the individual data sets have kind of a moderate amount of variance, but the aggregated data, when I combine all of them together, is going to have a much larger variance. And that's really the idea here, is that kind of if we have three populations that to themselves have a reasonable amount of variance, they're kind of reasonably well behaved. If the means are all the same, the X bars will all be probably close to one another. And when I aggregate the data, when I combine them into one big data set, the variance will still be a moderate size. If one of the data sets has a mean that's way different than the other two data sets, then that one data set, basically all of its normal data, are going to look like outliers from the perspective of the other two data sets. And in a sense, when we aggregate them, we'll have a bunch of outliers, which will dramatically increase the variance. So the individual data set on the right side, the individual data sets will have a moderate amount of variance, but the aggregated data will have a much higher variance. This is the important idea. We're analyzing variance, the kind of within the data or within the group variance versus the across all of the groups variance. We're analyzing those two variances. Is the aggregated variance much larger than kind of the individual variances? If it is, that might point to at least one of the means being different. And if it's not, that might point to the means being all the same. Okay, so I kind of wrote out some notes down here. Again, on the right, from the perspective of populations 2 and 3, essentially all of the data points from population 1 are outliers, this will dramatically increase the overall variance. As I alluded to before, because ANOVA is used in a lot of different fields, there's some different terminology for these. The different populations are sometimes called groups or treatments. You know, if we're using different, say, pharmaceutical treatments or something on different strata, or sometimes called factors. I think in psychology they often talk about factors. I think they might actually call this whole idea factor analysis or something like that. There's the idea of the so-called total sum of squares, or roughly speaking, the total variance of the sample when all the populations are combined together, when everything is aggregated together. That's the total sum of squares. And we're going to denote it SS, although unfortunately sometimes it's denoted SST, again, depending on what situation you're in. There's the within treatment sum of squares, or within group sum of squares. This is usually called SSE. And this is the sum of the squares due to sampling error. This is analogous to the idea of the variance within each population sample. And then there's the between treatment sum of squares. This is the contribution to the overall variance, the contribution to this total sum of squares due to the differences in the treatment, due to the essentially distance between these distributions, say on the right-hand side up here. And one of the nice things is that, just mathematically speaking, the total variation, SS, this total sum of squares, can be broken down into two components that are the sum of the other two. SSE, the within treatment sum of squares, plus the between treatment sum of squares. So roughly kind of what we're saying, and we're saying all of this in terms of sum of squares, but we're kind of thinking of it roughly in terms of variances. We're kind of roughly saying that the total variance is the within each group's variance plus the contribution of the variance from potentially the groups being located at different points, centered around different means. If the groups are not centered around different means, I would expect that SST would be kind of small relative to SSE, and the SS would basically look like SSE. If these groups are spread apart, if the means, or at least one of the means, is quite different from the others, I would expect SST to be large relative to SSE, and I would expect SS to be significantly larger than SSE. So again, roughly speaking, that's kind of what I said here. If it's true that SST is large relative to SSE, or in other words, if it's true that the total variance of the aggregated data is quite a bit larger than the kind of within group variances, then we think that the contribution to the variance from the groups being located at different places, centered around different means, is large. And I would want to reject the null that the means are all the same in favor of an alternative where the means are not the same, where this contribution from SST is large because these are actually centered around different population means. So let's consider a test statistic, kind of like a Z observed or a T observed or a chi-squared observed. This test statistic is going to be called F. We're going to use a different distribution for it, but it's just the F distribution. It's like the chi-squared distribution, kind of. And it's going to be the ratio of SST to SSE. Now remember what we said, if SST is large, the sum of the squares between the treatments are due to the difference between the means and the treatment groups. If it's large relative to the within group sum of squares or within group variance, then we reject the null and we conclude that the means are not all the same. Otherwise, if f observed is not large enough, we fail to reject the null. This is a right tail test. Because again, we reject the null, we conclude that the means are different, that the groups are spread out, only if essentially the variance between the treatments is a large contributor to the overall variance, or is a decent bit larger than the variance within each of the groups. So what does the sampling distribution of F look like? Again, I said it's kind of more or less SST over SSE. It turns out that it needs to be SST over this letter here. Typically, these letters are written as nu. This kind of curly V, that's the Greek letter nu, the Greek letter N. So SST over nu1 over SST over nu2, or MST over MSE. And I don't know why this one is not italicized. There we go. So here nu1 is the number of treatments minus 1, the number of groups minus 1, or number of populations minus 1. In this case, it will be 3 minus 1, or 2. And nu2 is the total sample size minus number of treatments. In this case, it would be, when we aggregate all of the data, it will be that sample size minus 3, because there are 3 treatments or 3 groups. And nu1 is typically called the numerator degrees of freedom, and nu2 the denominator degrees of freedom. And it kind of makes sense, right? The numerator is looking at SST, the sum of squares between treatments. So it's kind of viewing the treatments as almost like the sample size. So it's like 3 minus 1. That's kind of in line with n minus 1. And total sample size minus number of treatments. Well, we need to have each mean be the same. So for each of the treatment groups, we lose 1 degree of freedom. If we look at F observed, again, we said that that's basically a ratio of 2 variances. But we also know that variances, if we think back to chapter 7, when we did confidence intervals for variances, we knew that confidence intervals for variances used chi-squared numbers. Variances were kind of more or less distributed like chi-squared numbers. If I have the ratio of 2 variances, 2 sample variances, it turns out to just more or less be the ratio of 2 chi-squared numbers. So the sampling distribution for F, this goofy new statistic that we just called F, what is it? It's really just the ratio of chi-squareds. And kind of strangely enough, a ratio of 2 chi-squareds more or less looks kind of like a chi-squared. So F has the same kind of distribution as a chi-squared. It's going to be right skewed. It has a hump somewhere in the middle, and it's positive, right? A ratio of 2 positive numbers. We know our chi-squareds are positive. Ratio of 2 positive numbers, of course, is positive. So F kind of qualitatively looks more or less like a chi-squared distribution, not really like, say, a normal distribution or something that would go all the way off to the left down to minus infinity as well. Okay, so a couple of side notes. What if we have 2 treatments or 2 groups? Well, we might be a little worried here. We have 2 different ways of deciding whether or not the means are the same, right? If I look at this hypothesis test, H naught mu1 equals mu2 and H1 mu1 not equal mu2. Well, we could use ANOVA, which we're developing now, or we could use testing for difference between 2 means from chapter 9. This seems problematic. Should I pick one or the other? Is one better than the other? Should I like do them both and see what answers I get and hope that they both match? Well, it turns out that they're actually exactly the same in the case n equals 2. And here's just a little bit of a note on why that is. I think for time considerations, maybe I'll skip over this bit, but this is just giving a short argument as to why they are the same. Importantly, nu1 equals 1. A chi-squared with 1 degree of freedom is just the square of a standard normal. So that's really the driving factor here. When we have two treatments or two groups, two populations, ANOVA and the t-test are exactly the same. They'll always give the same result. Now they'll give a different number for F observed versus T observed, and you'll get a different number for F critical and T critical maybe. Your F will be like the square of the T, but the end result where you say reject H naught or do not reject H naught will always be the same. But so why use ANOVA then? Well, because with ANOVA, we can do the same thing with more than two populations. ANOVA generalizes the t-test for the difference between two means to 3 means or 4 means or 10 or 20 means. We can do as many populations as we want now. Well, we might ask ourselves then kind of the same question that we asked with the chi-squared goodness of fit test. We said, well, I mean, if I'm rolling a die, I can use just the basic chapter 8 hypothesis test for probability of rolling a 1. Is that, 1/6? But then I could just repeat that. I could just do 6 of those hypothesis tests side by side. Why not just do that? Why do this chi-squared goodness of fit test? It's the same argument here, right? Why not just use several t-tests? I could do a t-test for is mu1 equal to mu2. I could do one for is mu2 equal to mu3 and do one for is mu1 equal to mu3. I could do 3 different t-tests and then just reject if any of them warrants a rejection. Well, the problem is that if I say I'm going to reject any time that I get a rejection under any of these 3 tests, well, the problem is if I make a false rejection 5% of the time here and 5% of the time there and 5% of the time there, well, then my type 1 error rate looks a little bit more like 15% than 5%. If I have more populations under consideration, it gets even worse. It's really closer to maybe 14.3%, but still, you're seeing that we're not controlling the type 1 error at 5% as we thought. It's starting to grow. So what ANOVA does is it compares all the populations at once and keeps that type 1 error rate at the 5% level. Okay, so let's look at an example of some output that we might get from Excel, and we're going to use Excel to do the legwork for these calculations, but we're just going to go through this table just to see how some of these cells relate to other cells. Also, unfortunately, depending on the software that you have, sometimes the tables you get are slightly different, so it can sometimes be a little bit of work to unwrap exactly what is being said, how it's being said. So what do we have here? We have a table that is partially, didn't want to do that, is partially filled in, but not completely filled in. And I have up here an example table. So this gives us our formulas for the different bits. So what can I do? Well, I can start working out the numbers that should go in this table down here based on some of these formulas. Now, these formulas that I've given up here are slightly different. They're from a slightly different table, as the table that I'm working with, just to illustrate that sometimes we need to be a little bit flexible in our thinking. I see I have between groups versus within groups variation, and I have the sum of squareds for treatment. That's the between groups one. So I see that the top row, the two top rows correspond, and sum of the squared error, that's the within groups variation. So the middle two rows correspond, and then of course my total at the bottom is just the total. I see that I have 23 degrees of freedom for the within groups error, this new 2. I would like to find new 1 and my total degrees of freedom. How can I do that? Well, I do see that if I can select these two, there we go. I do see that MS is SST over new 1. So if I go back up, I see that SST, the total sum of squares, is also denoted SS. So this is where it's kind of unfortunate that we have SST used in two different places here. We have to kind of untangle what we're talking about. But we see that when we're talking about SS, that corresponds to SST. Okay, so my MS is SST over new 1, or my 0.612 is 1.224 over new 1, over the treatment degrees of freedom. I can multiply by new 1, divide by 0.612, and I get a new 1 of 2. So I have 2 treatment degrees of freedom where there are 3 groups, there are 3 populations I'm considering. My total degrees of freedom is 25. So I have that over here. I see that F observed is MST over MSE. So what is that? Well, 0.77 is MST, 0.612, over MSE. That's this number that I would like. This one that's below 0.612. Or I see that MSE, I can multiply through by MSE, divide by 0.77. And I'll come over to my calculator. I know it's off screen, but I'll just do this quickly. 0.612 over 0.77 gives me 0.795 or so. And then lastly, SSE, the one that's below this 1.224. I know that MSE is what SSE over nu 2. That is just this formula. Or I know that MSE is 0.795. That's going to be SSE over nu 2 is 23. Or SSE is 0.795 times 23. And again, I'll just do that off screen here really quick. That's about 18.3 or so. Now the question is, how do I find the p-value or the critical number? I have an F observed. I know it's a right tail test. So I reject if either P is less than alpha or F observed is bigger than F critical. right? These both should give the same answer. So how do I find those? Well, short answer is I use Excel. I can use Excel to find these. We're not going to go through how to compute these explicitly in Excel. If we had a little more time, I might show you how to do that, but we're just going to jump over to Excel and look at example output. Okay, so let me just stop the share here for a minute. I'm going to put an Excel file into the chat. Okay, so I popped an Excel file into the chat for ANOVA examples. So if you want to follow along, you can open that up. Okay, and here we have two examples. We'll start with example one, measure for elasticity in plastic produced by two different processes. We have process A and process B, and we have some sample elasticities for plastics produced by each of the two processes. And again, our question is, do we think that the mean elasticity for plastic produced by the two processes is the same in light of these two data sets? We could make two box and whisker plots, and at a glance, I think we would say, yeah, I mean, it seems pretty reasonable that they would be the same. But again, at a glance, that's not very scientific. That could be misleading. It's hard for us to assess whether a change could likely be due to sampling error or not if we don't actually run the numbers. So what could we do? Well, for this problem, we actually could, if we wanted to, use the chapter 9 method, right? We just have two populations. Let's actually do that just to kind of remind us how that works. We would get two X bar observed, two sample standard deviations. This would give me a T observed. This would be the difference between, essentially the difference between the two X bar observed, right? It will be X bar 1 observed minus X bar 2 observed minus the null hypothesized mu1 minus mu2. But under the null, those two are the same. So those mu's drop off. So we just end up with a numerator of the difference in the X bars. And then over this long thing, that's the square root of the sum of the variances, the sum of the standard errors squared. That ends up giving me about negative 1.7. In the T world, this will be a two-tail test, testing for whether the means are different or not. Not in the F world, not in the ANOVA world, but in the T world. So we'd have a T critical of 2.22 or so, but plus or minus. And negative 1.69 is not to the left of negative 2.22, and it's not to the right of positive 2.22. Therefore, we don't reject the null in favor of the alternative, and we would move forward under the presumption that the means are the same. Now, what would an ANOVA look like? When we run ANOVA on Excel, we would get an output that looks something like this. Again, we should recognize this, this table here. Let's see how we get this data, this table. Well, we go up to our data menu. We go over to data analysis, the same that we did for like regression recently. Down here, we see our regression, but we're going to do single factor ANOVA all the way at the very top. ANOVA single factor, don't pick the other ones, the two factor ones, just single factor. My input range, I'm going to choose A and B. I will make sure that I tell it labels in first row. These are grouped by columns, like A's population data, or the A population sample data is in the A column, and the B population sample data is in the B column. It's not grouped by rows, so we'll leave it as grouped by columns, and we'll output in a new worksheet. So I just select my data, make sure that it's arranged the right way. Make sure I choose labels in first row. Here, my alpha is 0.05. I'll just leave that alone. And you see it gives an output that is basically the same as this one here. We have some sum of squares. We have degrees of freedoms. Our new one is 2 minus 1, 2 groups minus 1. Our new 2 is, well, we have 12 total data points minus 2 groups. That's our 10. We have 11 total, 10 plus 1 degrees of freedom. So we see that all these numbers match up with what we would expect. And here we have an F observed and an F critical. Remember that in the F sense, the F test sense, the ANOVA sense, this is always a right tail test. So we ask, is 2.87 bigger than 4.96? And the answer is no. We're not in the rejection region. We do not reject the null hypothesis that the means are the same. We could alternatively look at our p-value. We get the same answer. We're testing against the an alpha of 5%. Is the p-value less than 5%? Well, no, it's 12%. That's not less than 5%. So we would not reject the null in favor of the alternative. As an aside, if you remember when I said that the F for 2 groups basically is just t squared, if we took our t observed and t critical numbers and squared them both, t observed squared to give me 2.87 or so, and that's just what F observed is. T critical squared 4.96, that's what F critical is for the 2 groups case. Again, why do ANOVA then if we can just use chapter 9? Well, that works for 2 groups, but if we look at example 2, we have an example with 3 groups here. We could have even more groups in other examples. So suppose we have some students randomly assigned to 3 different teaching methods, and these are their grades on the same exam given to the 3 different groups. So 3 groups of 5 and 3 different teaching methods. And again, if we just look at the box and whisker plot, like at a glance, I would think that method 2 and method 3 are pretty similar, and maybe method 1 is worse. Maybe method 1 is different. So what is my ANOVA test? It's going to have a null hypothesis that the means are the same between the 3 methods, and an alternative hypothesis that at least one of the means is different. Again, I could go through that same process. Go to data, data analysis, ANOVA, select my data, and so on. And I would get an output that looks like this. And I see my table that I should pretty much recognize. And again, I asked my 2 questions, or really I need to ask one of them, but it's not a bad idea to look at both just to make sure that you didn't make a mistake. I have an F observed and an F critical. This is a right tail test. F observed of 4.1 is to the right of 3.88. F critical, it is in the rejection region. I would reject H naught in favor of H1, and I would conclude that at least one of the 3 means is different from at least one of the other 3 means. Similarly, I look at my p-value. Using a significance level of 5%, the p-value is 4.4% or so. That is less than 5%. That's p is less than alpha. So I would reject the null in favor of the alternative. I would conclude on the basis of this test that at least one of the means is different from at least one of the other means. Now, maybe looking at the data, I would strongly suspect that mean 1 is less than mean 2, and that mean 2 and mean 3 are equal. But I didn't actually prove that. I didn't actually demonstrate that statistically with ANOVA. All that ANOVA has said is that at least one of the means is different from at least one of the others. I would probably strongly suspect, looking at this, that mean 1 is lower than mean 2, and mean 2 is maybe about the same as mean 3. But ANOVA didn't tell me that. ANOVA told me that I have statistically significant evidence that at least one of the means is different from at least one of the other means. And that's all that it tells me. Everything else from there is kind of a qualitative judgment, based on looking at this. So that's as far as we're going to go into ANOVA. And that finishes up our discussion of ANOVA, finishes up the material for the course. Does anybody have any questions on anything from today, anything about the exam, anything else? Okay, then it's been a